Scientists study the natural world using the scientific method. But the scientific method didn't spring forth fully formed. It's not at all an intuitively obvious process. In fact, it emerged gradually as humans began to realize the great scientific principle that many aspects of the physical universe are regular and predictable. In this lecture, I want to tell you about the slow but seemingly inexorable path towards our present view that the universe is governed by a few great overarching natural laws. But first, I want to look at the scientific method in somewhat more detail. Recall that the scientific method has 4 parts. First, you have observations, you have experiments, you collect data about the natural world, and you systematize this data in tables. And then second, you begin to see patterns. You begin to see systematic behavior in those data. And this leads to the third step. That's hypothesis, theory, making up natural laws. But every hypothesis, every theory has to make predictions, and that's the 4th step in the scientific method. You make predictions, and then you can go out into the natural world and you make more observations, you conduct more experiments, and so the cycle goes on and on and on continuously. Well, that's the idealized scientific method. But scientific discovery seldom follows this exact idealized path. So I want to look at the scientific method in a little bit more detail in some of the classic examples. Even the case of Dmitri Mendeleev and his discovery of the periodic table doesn't really follow that exact pattern. Let me tell you why. Mendeleev had 63 chemical elements. Those were his data. And he saw patterns in those data. He saw systematic trends. And so, for example, rubidium, potassium, sodium, 3 elements that are all soft, silvery metals. They all react violently with water. They all combine with chlorine and fluorine in 1-to-1 ratios. These he grouped together. He said they're going to be a vertical column of elements because they're so similar. But Mendeleev had to ignore equally obvious and compelling similarities in other elements. For example, think about iron and cobalt and nickel. These are all silvery metals. They're all quite hard. They all react in a 1-to-1 ratio with oxygen. They're all magnetic, and that's a striking property because very few chemical elements are magnetic, but all 3 of these are. And yet, Mendeleev put these 3 elements side by side in his table. He ignored their similarities and did not put them in a vertical column. So he had to have some kind of intuitive hunches about how you put the table together. It was not just a straightforward process. It involves some creative leaps. Another great example of an intuitive leap is that of Isaac Newton and his understanding of the motions in the heavens and on Earth. In the 1660s, Newton's contemporaries saw all the motions of planets and stars in the heavens as one sphere, as one domain, completely distinct from motions on the Earth. But Newton had another intuitive idea. He said, perhaps these motions are in some way related. Perhaps when you drop an object and gravity brings it down to Earth, and then when you throw an object, it adopts a curving path. But if you could throw it really hard, if you could take an object and throw it as hard as you possibly could, so it actually went into orbit around the Earth, then it would adopt the same curving path that you see characteristic of the moon, of the stars, of the planets. And so Newton, unlike any of his contemporaries, saw that similarity. He saw the connection between motions on Earth and motions in heaven. That was a great intuitive leap. No one else had ever seen the universe that way. These stories of intuitive leaps often take on mythic proportions. You have the story of Einstein sitting on a trolley car in Switzerland, receding from a clock tower and thinking about relativity. The story of Newton, of course, sitting in an apple orchard with the apple falling. Some people say it fell on his head. Of course it didn't, but that's the story. Scientists claim to have these intuitive moments, these great insights in the shower. They have them in dreams. And it's always this critical nonlinear aspect of the scientific process that's involved, something you really can't legislate by a strict scientific method. Science is intensely creative. You know, I'm often amused at people's reactions when they find out that I'm a musician. I play trumpet in a symphony orchestra. And people say, oh, you must be so creative because you play a musical instrument. And it's just absolutely not true. Music is a discipline. When I go into an orchestra, I have to play the notes that are on the page. I have to play when the conductor says. I have to play at the dynamic the conductor says, because a trumpet player gone awry who's too creative can really wreak havoc in a symphony orchestra. Well, that's the discipline in my life. But science, I go into a laboratory, and think about it. I've got chemicals, I've got apparatus, I can do anything I want to. Nobody's telling me the next experiment to run. Nobody's telling me how to synthesize that data. And so science is intensely creative because you have to constantly make it up as you go along. And the scientific method only gives you the loosest, vaguest sort of guide as to how you might do that. There are other human aspects of science that add to its interest and complexity. One is that scientists often make mistakes. But science is a self-correcting process. It's a collective process in which anytime you make a finding, someone else is going to come along and try to verify that finding. Honest errors in technique and execution are just part of the game. It's inevitable. The demand for reproducibility eventually corrects and eliminates these mistakes. There's a great example. It's provided by a recent report that came out of Tulane University in the chemistry department. They published a very widely cited report about the intensified environmental effects when you combine certain pollutants. And here's the situation. If you have 1 part in a million of pollutant A, it becomes dangerous. If you have 1 part in a million of pollutant B, it becomes dangerous. What the Tulane researchers claimed is if you put the 2 chemicals together in much lower concentrations, they were, because of their combined effects, much more dangerous than they would be individually. And this is a terrible problem, for example, for the Environmental Protection Agency, because EPA sets toxicity limits for various chemicals. But imagine if you not only have to define the toxicity of thousands of chemicals, but then every possible combination of those chemicals. You get millions or billions of different combinations, and it's just an impossible task to identify those risks. So this was big news. They published the article, but then they tried to reproduce it and do more experiments, and the Tulane researchers themselves were unable to do it. So after all this publicity, they had to retract some of their findings. That's what scientists should do, but nevertheless, certain science journalists accused them of fraud. Well, this was not fraud. This was just the normal process of science. Every complex experiment has many variables, many things that are difficult to control, and sometimes procedural errors happen. It doesn't constitute scientific fraud. It's just a part of the process. Later in this lecture, I'm going to tell you about the famous case of cold fusion, in which 2 Utah researchers claimed that they had a new source of energy. Well, they were wrong, and they were justly embarrassed, but once again, this wasn't fraud. This was just the kind of error that humans make, and the kind of error that humans become very embarrassed once they do make. Having said that, I really should address this question of scientific fraud, because once in a while, there are cases. It's rare, but it does happen. And once again, the scientific method is a correcting process. So I want to tell you the story about an American paleontologist named Albert Karl Koch, who lived in St. Louis in the 1830s and 1840s. Here's a good example of a fraudulent bit of science. In this period, in the 1830s and 40s, there were fossil bones in rich abundance in various remote parts of North America. And Albert Karl Koch made it his passion to go out with an ox cart and just ride along the countryside, find one of these deposits, and fill up his ox cart with fossil bones. For example, he had fossil bones of mastodons and fossil bones of whales. He'd pick up bones, some of them 6 or 8 inches across, some of them vertebrae up to a foot or more across. He'd bring them back to his St. Louis museum, where he charged admission for the various exhibits that he put together. Let me read you a quote by Koch, who describes this collecting process. "The place where those relics were deposited is one of the most romantic situations I have seen in Missouri. The bones in general have been broken. Those that have thus far been disinterred consist of, at first, the head of an undescribed animal. from which it appears that it exceeded the elephant in size from 4 to 6 times. This is in one of Koch's scientific publications. What Koch had done is he'd gotten as many bones as he possibly could, many vertebrae, many ribs, and then he'd stack them together end to end. He'd make long chains of them, as many vertebrae as he could, from all different species. He'd stick them together. He'd make the most outrageous concoction he could. Indeed, organisms that were much larger than the elephant today. He would make fossil sea serpents, stringing hundreds of vertebrae together, making individual fossil skeletons more than 100 feet long. And he could charge admission for these, 25 cents, 50 cents. That's a lot of money in those days. And people would flock to see these remarkable, fanciful reconstructions. Koch abused the scientific method. His data were the bones. His hypothesis was these reconstructions that he knew were false because he had taken bones from different places, strung them together in ways that weren't physically impossible. And yet, scientists saw these, they denounced the reconstructions, but they purchased his fossils from him. They took them back to museums, and they reassembled them in ways that were correct, that were anatomically reasonable. And you can go to museums today, to the British Museum, for example, and actually see some of the bones that Albrecht Karl Koch collected, because science is a corrective process. The data were still good. They were assembled in a non-fraudulent way by the museum, and now we can benefit from Koch's collecting. No matter how compelling a theory is, it has to stand up to repeated tests, to scrutiny of the scientific community. And here I want to come to a central point. Science is not a religion. Scientific truth is based on independently verifiable observations, on experiment, and on logic. But scientists do share a belief. They take it on faith that our senses do not lie. What we see, what we touch, what we smell, what we hear, these are truths. And if I can verify it and you can verify it independently, that has a kind of truth to it. You can make a measurement, I can repeat that observation, and our answers should match within reasonable experimental error. In the long run, fraud in science, therefore, just doesn't pay. Let's take a closer look at this central belief or assumption of science. To modern scientists, each observation and each measurement represents an objective, verifiable truth. Each measurement thus has meaning. But the importance of observations has not been at all obvious or widely accepted in earlier times. The Greek philosopher Aristotle, who lived from 384 to 322 BC, is a good example of this. He was a student of Plato. He was a tutor of Alexander the Great. Certainly he recognized that the senses play a very important role in understanding the natural world. But to him and to his followers, logic and reason, rather than our fallible senses, were the ultimate arbiters of truth. It was the brain, not the hands, that led to an understanding of the natural world. In the words of the British historian Neville Andrade, quote, Aristotelians considered that knowledge about nature could be won by pure thought, and that experiment was, in a way, a rather trivial and pedestrian proceeding. Many scholars prior to about 1650 accepted the writings of Aristotle and other ancient authorities in preference to observations. In our textbook, The Sciences, Jim Treffel and I recount a story about a debate at Oxford College that occurred during this period. And this debate was about the number of teeth in a horse's mouth. One scholar quoted Aristotle. Another countered with a different opinion from the theologian St. Augustine. And so forth, back and forth the debate went. Eventually, so this story goes, a young monk at the back of the auditorium got up and noted that since there was a horse outside, they could just go out, look in the horse's mouth, and count the number of teeth. At this point, records claim, the assembled scholars, quote, fell upon him, smote him hip and thigh, and cast him from the company of educated men. The great Italian scientist Galileo Galilei met a similar kind of response in the early 1600s when he first used the telescope to look into the heavens. Galileo had heard about the telescope as a Dutch invention. He made his own in 1609 and focused it on various objects in the night sky. He discovered supposed imperfections in that night sky. He found moons orbiting Jupiter. He found sunspots. He saw what appeared to be a vague fuzzy mass around Saturn, what later turned out to be the rings of Saturn, and so forth and so on. Craters on the moon, mountains on the moon, imperfections in what should be perfect spheres in a perfect heaven. Historian of science Giorgio de Santillana writes, quote, Galileo had thought the discoveries of the telescope would provide irrefutable proof to any man in good faith. But a few months were enough to undeceive him. Certain doctors steadfastly refused to look through the telescope. Some did look and professed to see nothing. Most of them, however, said that they had never gotten around to looking through it, but that they knew already that it would show nothing of philosophical value. Let's shift gears now and look at the nature of predictability in the universe. While many scholars have questioned the reliability of the senses, everyone relies on some extent or another on the predictability of the physical world. The simplest kind of verifiable observations are events that happen over and over and over again, things that occur in our lives with regularity. Long before science, humans developed an absolute dependence on certain repeating patterns in nature. For example, the way objects fall and the way they move when they adopt curving paths through the air is absolutely critical to a hunting society. So if you take an object and drop it, you have confidence that it's going to fall. If you take the object and drop it again, you say, it fell again. There's a repeating pattern. Or when you take an object and throw it, it adopts a certain kind of curving path. If you take another object and throw it again, it adopts the same kind of curving path. And you rely on this, for example, if you're a spear thrower, you're hunting game, you rely on that ability to throw things in the same kind of arc again and again and again. This is vital to the survival of any people. Most astronomical objects also have predictable paths. The sun rises and sets each day, while its position in the sky and the lengths of the day change in a regular pattern from season to season. The moon also changes position in a regular fashion, and it also passes through a predictable 29-day cycle of phases from new moon to full moon, back to new moon, and so forth. You can measure these changes yourself, and you can do it in a very simple way. This is a wonderful thing to do with your children. If you've never studied the phases and the shifting patterns of the moon, it's fascinating to do this, and you can graph your results in a very simple way. Let me tell you how to do this. Pick a time of day. My favorite is 7 a.m. or 7 p.m. Since the moon changes its position systematically, some weeks you're going to have to look in the morning sky, some weeks in the evening sky to see the moon. And here's what you do. You pick that time. You have to have an accurate watch. Always do it at 7 o'clock on a particular day, if you choose that time, or 8 o'clock or 9 o'clock, whenever it's convenient for you. Take a compass. Sight the direction to the moon and take a compass reading from north, a certain number of degrees to the west of north or to the east of north. That's where the moon lies in the sky. That's the first number you need. That's a number along the horizon. And the second thing you want to do is measure the height. And the easy way to do that is to take a protractor that's marked off in degrees. I like to tape a straw to the edge of the protractor. That gives you something to sight along. You then take the protractor, you sight up to the angle of the moon, and let a little weight hang down. And then just hold that weight and measure the angle. Do this day after day after day. And you can plot these results, these two numbers, the angle from north, the angle up from the horizon. You can plot them day by day on a piece of graph paper, and you'll see the repeating pattern of the moon. Note its phase also, because the moon will change from new to half to full to half and so forth. Day by day, you'll see those changes. This simple exercise repeats what has been done for thousands of years by ancient astronomers all over the world. It's a very simple observation that, in spite of our modern technological society, it's still worth doing today. Some ancient societies displayed their belief in the predictability of the heavens by constructing large monuments in which the position of massive stones were aligned with key events in the sky. One of the earliest examples of human faith in this regularity lies at Newgrange, Ireland, about 40 miles north of Dublin. There you can find the remarkable 5,000-year-old burial tomb of an ancient Irish leader. The tomb's in the form of a burial mound. It's constructed from a huge pile of heavy stones, and the burial chamber itself is 69 feet deep inside this mound. At dawn, on the winter solstice, that's the shortest day of the year when the sun finally begins to track back after the days have gotten shorter and shorter and shorter, you see a long, narrow channel, and that shortest day, the sun's rays enter, right at sunrise, the sun's rays enter that long channel, and they shine down 69 feet onto a rock with rock carvings right at the very center of the burial chamber. To build that chamber required tremendous effort and ingenuity, and it required faith that year after year after year, the sun would rise at a certain point on a certain day. Stonehenge is another example. It's a great monument on England's Salisbury Plain in southern England. It served as an elaborate and sophisticated calendar. The agricultural community that labored to erect this great mass of stone, the great trilithons with 2 verticals and a horizontal lintel that weighed many tons, that great effort served to cite certain key times of the year: sunrise, sunset, moonrise, and moonset on certain key days. And you could, by sighting through the arches at more distant stones, at wooden pillars that were put around at various points that monument, you could basically keep time in the year. It was an astronomical calendar. There's a wonderful book about this subject, about Stonehenge. It's Richard Hawking's Stonehenge Decoded. And in this book, Hawkins presents the theory that they could actually produce lunar and solar eclipses using Stonehenge. It's a fascinating idea, and certainly it's well worth a read if you're interested in those additional aspects of Stonehenge. But in any case, Stonehenge shows that ancient peoples recognized regularities and predictabilities in nature. Science depends on maintaining meticulous records of observations, and so we're going to fast forward now to the time of Gaius Plinius Secundus, who lived from 23 to 79 AD. He is best known as Pliny the Elder, and that's to distinguish him from Pliny the Younger, who was his nephew. Pliny the Elder led a rich and varied life. He was a cavalry officer in Rome's colonies in Germany. He served as a naval commander in Naples. For a time, he was a lawyer. He also was an administrator to Rome's Spanish colonies, so he really got around ancient Rome. He's best remembered for his encyclopedic Natural History, a compendium which is divided into 37 books, each of which tabulates the facts that were known to him directly or through respected authorities of the time. Topics range from a systematic catalog of all the known plants and animals, minerals, to various recipes for medicines and for manufacturing processes. This natural history is quite unusual, and it's the first book that actually cites references. It has over 100 references to 100 noted authorities. This work provides an unparalleled view of knowledge at the time of the early Christian era, but the result is often an uncritical mix of facts and myths, superstitions. Pliny's translator, Professor Rackham of Christ's College, Cambridge, describes the work as follows. He says, Pliny claims in the preface that the work deals with 20,000 matters of importance drawn from 100 selected authors. In selecting from these, he has shown scanty judgment and discrimination, including the false with the true at random. His selection is colored by his love of the marvelous, by his low esteem of human ability, and his consciousness of human wickedness. In his section on gemstones, for example, Pliny claims that quartz crystals form from intense freezing of moisture from the sky. Amber, he says, is a prophylactic against tonsillitis and other afflictions, and diamonds can be fractured by soaking them in goat's blood. There are also many facts that we would now counter as true, so there's a mixture in there. Pliny died, by the way, while observing an eruption of Mount Vesuvius in AD 79. This is the same eruption that destroyed Pompeii and Herculaneum. He first approached the volcanic eruption out of curiosity. He wanted to see what was going on. But when he got near, he was trapped because the seas became violent, there were earthquakes, and he died of asphyxiation while trying to comfort other victims of this disaster. Pliny's work, his natural history, represents an essential step, an essential aspect of science, collecting data. But it really wasn't the scientific method. So I want to look now at one of the first clear examples of the scientific method in action. To many ancient cultures, knowing the positions of the moon and the planets was of great importance, both for astrological predictions and for navigation. Those two reasons why you'd want to study the skies. The thousands of visible stars form this constantly rotating backdrop of constellations. And against those constellations, you see night by night the movement of planets, the wanderers. One of the most complicated things about the movement of planets is that they have retrograde motion. If you plot the position of the planets against the stars night after night, you see the planets moving forward, then they sort of slow down, and for several weeks or months they move backwards against the then they start going forward again, but then they slow down and start moving backwards. This retrograde motion had to be explained by any model of the universe. One of the first descriptions of the universe that led to testable predictions was the extremely successful model of Ptolemy of Alexandria, who lived from 100 to 170 AD. He was an Egyptian-born Greek. He collected many of his own observations about the heavens, as well as compiling those of earlier Babylonian and Greek astronomers. He compiled all this information in a 13-volume work called the Almagest. It's a lengthy treatise, and it's best remembered for the Ptolemaic model of the solar system. Ptolemy argued that the Earth had to be at the center of the solar system because otherwise, if the Earth moved around some other object, the atmosphere would be stripped away. The Ptolemaic model postulated perfect circular orbits, but inside those orbits were smaller circles called epicycles, which explained the retrograde motion. This use of circles was absolutely dictated by the idea that the heavens were perfect and the circle was the only perfect form. Milton, the great poet, captured the complexity of this system in famous lines from his Paradise Lost. Let me read you this quote. "How they will wield the mighty frame, how build, unbuild, contrive to save appearances, how gird the sphere with centric and eccentric, scribed o'er with cycle and epicycle, orb in orb." Give you a sense of the artificial complexity of this model. Yet in spite of its complexity, the Ptolemaic system was reasonably successful in predicting planetary positions, and it survived for 1,400 years. That's probably the longest running scientific theory in history. You could, using this Ptolemaic method and extremely laborious mathematical calculations, predict the position of a planet at some future time and place. It was not until the 1500s that a new, more precise set of observations and the application of the scientific method led to a general acceptance of a competing theory. In summary, this lecture, we've seen that the scientific method is a richly varied human construct. It seldom operates as a simple cycle. Human intuition and imagination, creativity, all play central and vital roles in the scientific method. The idea of a regular and predictable universe with overarching laws to be discovered by observation and by experiment was not at all obvious to ancient societies. Aristotelian philosophers favored pure logic over experiments in understanding the world. Nevertheless, mathematical models of the solar system, notably the Ptolemaic Earth-centered model, displayed a faith in the regularity of nature. In the next lecture, we're going to see how the Ptolemaic view was eventually replaced by the Copernican model.